Alright, so let's start the 25-minute timer. Actually make the deadline 20. See if we can solve this question in 20 minutes. Okay, so we've got a round table with n people sitting around it. So we're going to have something like this, where each smaller circle represents a person, and we'll just assume there's n people. Not assume, it's given in the question. This question is asking us, what is the probability of person A sitting exactly k seats away from person B? Okay, so how are we going to do this? Let's just choose person A and person B at random. So if we assign a number to every single one of these seats, we'll start at 0 here, and we'll just go 1, 2, 3, 4, 5, on and on and on, all the way around the circle till we get to n over here, at the n minus 1 and n. Okay, so now what we can do is we can say person A, we can assign A to be a random number between 0 and n inclusive. I'll use these brackets. This is some weird notation, but I'll let it be. And we'll also assign B to be a random number between 0 and n. So essentially, we're just picking out random numbers between 0 and n inclusive. And now the question is asking us, we want the probability, let's do it over here. We want the probability that, well, to sit k seats away, now that we've represented it numerically, if we were saying person A sits 3 seats away from person B, that means we want the difference between person A. For example, if I put A as 0 and B as 3, this would count as 3 seats. 1, 2, 3. So what we're saying is we want the absolute difference between A and B to be equal to k. All right, there we go. So, and that's what we're trying to find. Probability person A sits exactly k seats away from person B. Yeah, this is what we want. Okay, so we've managed to represent this situation sort of numerically, and this expression will work fine, but let's say we're going from, if we set A is equal to n, and let's do a different color. If we set A equal to n and B is 0, well now these two are actually 1 seat apart, but if we use this formula, we're going to get their n seats apart, which it's because we're looking at this direction rather than going forward in this direction. So how could we get around this issue? Right, okay, let me try represent this situation in a different manner. Probability of person A sitting exactly k seats away from person B. So let's put them all on a number line instead. We'll start at 0, 1, 2, 3, 4, on and on until we get to n. Okay, so now if we pick A and B at random, say A is 1, B is 3, then, okay, so let's just, for an example, pick k as 2. So now we're looking for the probability that A is 2 seats away from B. Okay. And the way to usually solve these kind of questions is to look at the number of possible combinations for AB. So these are the number of possibilities that, like this set of all possible values, if that makes sense. So all of the possible combinations of A and B, well, this is going to start from, does it say there's different probability of person A? Okay, so it's implied that A is not equal to B because there's people sitting around a table. You can't have more than one person sitting in a single seat. So we're told that A is not equal to B. I should put this in the conditions over here. And okay, so now all of the possible conditions for A and B, well, we could have A as 0, then B could be 1, B could be 2, B could be 3, all the way until B is n. And then we could repeat the same thing with A as 1, this time start as 0. You can't have 1, 1, but we can have 1, 2, on and on. So you can see there's ultimately going to be n choices for A and n minus 1 choices for B. I'm just trying to think if this is symmetrical. So can we get every single possible combination? Yeah, I believe we could. And this isn't going to double count things like 5, 5, because this can't happen. So I suppose what we're actually counting is just all of the numbers from 1 to, it'll be n, wouldn't it? All right, so that should tell us that the number of possible combinations, AB combinations, is equal to n times n minus 1. I think that's correct. It just seems a bit weird because it's not fully symmetrical for A and B, but maybe I'm just thinking about it weirdly. So we can test this. If n was, let's say, 3, that would say there was 6 possible combinations, and I guess we can just list them all out here. So we could have AB as being 0, 1, 0, 2, and 0, 3, because if n was 3, the final item would be 3. Oh, wait. Okay, I see the issue. If n is 3, the number of seats is 3, we can't really start at 0 because now we're going to have 4 seats. Okay, yeah, that's an issue. So let me just scribble this out. We'll kind of start the problem again, but this time just start at 1. 1, 2, 3, 4, on and on until we get to n. Okay, so now if n was 3, we'd effectively stop there. We can have the AB combinations, the different people's seating, 1, 2, 1, 3, and then we'd go 2, 1, 2, 3, 3, 1, 3, 2. As you can see, there's going to be, well, for every, at the start we have n combinations for A, and then for B, we can have, once A is fixed, we have n minus 1 possible choices for B. So this makes more sense now. The number of possible AB combinations is given by n minus 1. Okay, now what we want to find is the number of valid combinations. I guess we could call them solutions. And a solution is valid when, this is where our condition comes in. So if we want A and B to be separated by 2 seats, by k seats, then we need the absolute value of A minus B to be equal to k. So for example, if k was 2, a valid combination might be A is 3, and B is 1. Because now, if we think about this, 1, 2, 3, 4, 5. If we have A is 3 and B is 1, well, there's 2 seats separating A and B, so that's a valid combination. So we need to figure out how many of these valid combinations out of n multiplied by n minus 1 there are. Okay, and let's just have a look at the original question. N people. So I'm assuming the answer is going to be something to do, a function of n and k. But let's just think about this. So draw out the number line again. Or maybe I'll turn it into a circle, actually. No, number line's fine. So 1, 2, 3, 4, all the way up to n minus 1, n. So if we put A over here, let's first think about the case when k equals 1. So how many valid solutions? Well, if basically we just need A to be here, and for every position of A, there are 2 possible solutions for B, aren't there? We can have B1 over here or B1 over B2 over here. And that's valid for any A. So we can literally select A to be here, and we could have B1 there or B1 there. So therefore, when k equals 1, the number of possible AB combinations, well, this is just equal to n minus 1, and we know the number of valid AB combinations is going to be, well, there's n places we could select A to B, so we'll immediately multiply by n, and then for each selection of A, we have 2 places we could put B to make it valid, right? So, for example, we could have A is equal to 3, and then to be valid, B would either have to be 1 or 5. And, oh, sorry, k was 1, so B would either have to be 2 or 4. And the nice thing about this sort of way of thinking is that it doesn't really, we don't have to account for the wrapping round, because let's say A was n, well then B would either be n minus 1 or it would just be 1. We don't actually have to determine the other value of B, we just have to know that there's 2 possible values. So that's good. And okay, so therefore, when k equals 1, probability person A is k seats away from person B is going to be equal to these number over these number, because we can assume every combination has the same likelihood of being picked, so there's no weighting going on here. Does that make sense? So that's going to be 2 over n minus 1 in this case. Now it'll be interesting to see whether this lines up for other cases, but let's pick a slightly more complex case. So let's say when k equals 3. Now we can actually think about it in the same kind of way. 1, 2, 3, 4, 5, 6, 7, all the way up to n. So, wait, let's just make sure that we're not missing any solutions here. We can pick where A is, and that will give us all our solutions for B. But will that give us all our possible solutions? Okay, yeah, I believe it will, because A is going to be put on every single spot, and then for every single possible position of A, we're going to get the corresponding position of B. So it makes sense that if we put A at 3, we could get one solution for B at 4, and then if we put A at 5, we'd also get another solution for B at 4. So this is essentially the same as selecting where B goes and then putting in A. But okay, that's good. Now, when K is equal to 3, well, that's going to mean if we put A at, let's put it at 4. If A was at 4, then there would still be 2 valid solutions for B, wouldn't there? There'd be one solution at 1, and there'd be one solution at somewhere over there. One solution at 1, and then one solution at 7. Now, we need to check whether the solution exists. So in our case, we're thinking about a super long line, so it doesn't really matter. But let's think about if n was small, like n was 5. So 2, 3, 4, 5. Now, you have to remember K is 3. I'll just write it again over here. If we select A as 2, then 1, 2, 3. So we'd have the lower solution, I'll call it BL, where we go left. This would be at 4, and 1, 2, 3. Our upper solution, BU, would be at 5. So they'd be at different positions. And I think it makes sense if you think about on a circle, no matter where you select A, there's always going to be another person K seats away. You'll just have to wrap around the circle a few times. So even if there are only 2 people in a circle, if we had A's over here and K would be, let's say 7, well, you can always count 7 times, just going up and down, like this until you get back to the other person. Now, the only place where there wouldn't be an extra solution is if BU is equal to BL. So let me try and make an example where that happens. Let's have, okay, so let's have a line of, let's have 6. 1, 2, 3, 4, 5, 6. And I'm going to try to put K as an even number. Maybe this will work. So, right, so if I put A over here, 1, 2, 3, 4. Oh, 1 second. 1, 2, 3. Okay, let's have K as 3. That'll give us That'll give us the case I'm trying to illustrate. So when K is 3, we're going to have the lower when we go to left, 1, 2, 3. B lower is going to end up at 5, and B upper is also going to end up at 5. So now what this tells us is when A equals 2, there's only one solution for B. So we're not going to get 2 extra cases like we did over here. And this might actually not be valid in certain cases, but we'll just ignore that for now. When A is, in this case, you can see there's only one solution for B at 5. Now there's not 2. So we need to subtract these cases somehow. So we can write number of valid solutions is equal to, well, generally it's going to be n multiplied by 2, except for cases where B lies on the same point. So how can we identify these cases? When does this happen? Well, okay, let's try and think about this. If we set A as 3, 1, 2, 3. 1, 2, 3. Okay, so I think we're starting to see a pattern. Okay, hang on. I think we're actually close though. So perhaps this happens when k is equal to exactly half of n. Because if k is equal to half of n, that means you're trying to go halfway across the table both ways. And if k wasn't half of n, then you'd have different distances, wouldn't you? But it happens when... Let me get rid of this. When k equals n over 2, the corresponding solution for b, or we'll say solutions for b, will fall on the same person going left and right around the circle. Hopefully that makes sense, because even if we pick anyone, if k is exactly the number of seats away from the corresponding person, if that is equal to half the number of people in the circle, then even if you go left, you're going to end up at the same person as if you go right, because the distance going left is exactly the same as the distance going right. And I can't see this happening in another case, because if, let's say, we had to travel this distance k, you'd get a different person if you go this distance, because it's not half the circle, so you not end up at the opposite end of a circle again. So I believe that makes sense. So what this tells us is, if k equals n over 2, there is only one solution for every selected A. There's only one, let's put B solution here for every selected A. Therefore, probability that person A is k seats away from person B is equal to, we can work out number of valid solutions in this case is just going to be n for the number of A selections multiplied by 1 for the corresponding number of B selections over the total number of combinations, which we saw earlier was just n minus 1. Okay, which ultimately gives 1 over n minus 1. So that seems like the final answer, and I'll write it up here. Let me try to use nice notation. So if k equals 1/2 n, it's going to be 1 over n minus 1. Otherwise, it's going to be 2 over n minus 1. I believe that is the solution, and I'll check now.